Yes, it is visible now.
1 second, sir. Still,
Yeah, start recording, then share the.
where it is record. Okay, option is direct is there now.
Direct to my computer.
Okay.
To my computer.
Screen sharing, 1 second, sir.
Yeah, now share the screen. Yeah, open. Yes, visible.
Yeah. Okay, sir. Thank you.
Yeah.
Less participants are there, sir. Can you send unit 5 recording and PPTs? Did not receive yesterday's PPTs of unit 1 and 2. Now in KMIT online, some data material is uploaded. Ma unit 1 to 4 5 are there in kmitonline.com. Go through that procedure and check it. You have all the 4 units you have. First unit, second unit, and fourth and fifth. Okay. Good morning, everyone. So now the fifth unit, second topic. Here we have totally 6 topics. In the second topic is surface integral. Before we have a line integral, we completed line integral. The underline integral, the formula is integral over C f bar dot dr bar. No, 15 unit is uploaded, ma. Check it properly. Otherwise, today one more time I will check after this class. If not, I will again upload that because I'm sure fourth and fifth both are uploaded myself. Okay. So integral yes f bar dot dr bar, that is under this line integral. Circulation, work done, these are the terms we are able to have. So this is comes under line integral only. We have important problems under work done. So we completed that. Now we are entering to the surface integral. Here an integral which is evaluated over a surface is called surface integral, and it is denoted by integral s f bar dot n bar ds. The integral which is evaluating over surface, so that is what it is called as a surface integral. And formula for this is integral s f bar dot n bar ds. Here n bar is the unit outward drawn normal. That means here we have to take surface integral can always be evaluated by taking its projection on any one of the plane. Okay. Okay. Surface integral can be evaluated by taking its projection on any one of the planes. So usually we need to take this projection when we calculating surface integral. So surface integral can be evaluated. We know that point taking projection. So suppose if let R be the projection of the surface in S in XY plane. So XY plane obviously Z is equals to 0. So in the formula is converted into integral S f bar dot n bar ds is equals to double integral over R f bar dot n bar the plane is on x, the surface is on xy plane, so dx dy by modulus of n bar dot k bar. Similarly, if it is in yz plane, the formula is integral is f bar dot n bar ds is equals to surface double integral of over r f bar dot n bar. Here yz plane means dy dz by modulus of n bar dot I bar. Similarly, if it is in zx plane, so integral as f bar dot ds becomes double integral over the region r f bar dot n bar dx dz by modulus of n bar dot j bar. That r be the projection, so which plane it is occupying, so we need to take that formula. This in this unit, first three topics what we have is line integral, surface integral, and volume integral. Same what we are learning here, applications under this, same we have in the next three topics: Stokes, Gauss divergence, and this Green's theorem. So same problems we have. If it is verify means we need to verify both sides. Evaluate means one taking left hand side, evaluating right hand side, like that. But what about the applications? Here we are applying same that we are deriving. Okay, so if you perfect on the surface, line, and volume integral, so then it is easy the next off. So first one of the problem here we are seeing, evaluate integral s f bar dot n bar ds. F bar is given as 18z I bar minus 12j bar plus 3y k bar, and s is a part of the surface of the plane 2x plus 3y plus 6z is equals to 12, located in the first octant. So first quadrant it is saying, usually we take as first quadrant as xy plane, and we the surfaces we are considering here phi is equals to 2x plus 3y plus 6z minus 12, and normal to this plane is del phi. That is normal, here we are calculating as del phi, grad phi, that is equals to hmm, grad phi is equals to I bar dou phi by dou x plus j bar dou phi by dou y plus k bar dou phi by dou z. So partial differentiation will get as del phi or grad phi is equals to 2i bar plus 3j bar plus 6k bar, that is phi is 2x plus 3y plus 6z minus 12. So that, and unit normal here we are calculating to this del phi, that is equals to, formula is e bar by modulus of e bar, so that is nothing but e bar is here del phi, so 2i bar plus 3j bar plus 6k bar by square root of 2 square plus 3 square plus 6 square, it is becomes 2i bar plus 3j bar plus 6k by 7, that is unit normal. Then this is a projection on xy plane, here we have to calculate. So then the formula becomes integral s f bar dot n bar ds is equals to double integral r f bar dot n bar dx dy by modulus of n bar dot k bar. So already we know that f bar is 18z I bar minus 12j bar plus 3y k bar. Then we calculating f bar dot n bar. So after calculating f bar dot n bar, that value becomes 1 by 7 into 36 z minus 36 plus 18y. So 6 we are taking common out, it becomes 6 by 7, 6z minus 6 plus 3y after simplifying f bar dot n bar. Then we calculating f, next we are calculating f n bar dot k bar. So n bar is given as 1 by 7 of 2i bar plus 3j bar plus 6k bar dot k bar, it becomes 6 by 7. Then given surface is 2x plus 3y plus 6z is equals to 12, but it is, why we are taking again given, here we need to evaluate double integral, right hand side we need to evaluate double integral r. When that evaluation we need limits also, for that we are taking this surface, but this surface we are projecting on xy plane, so z value becomes 0, then it becomes 2x plus 3y equals to 12. In this we calculating y value, it becomes 12 minus 2x by 3, and this is becomes upper limit. Then lower limit as this is upper limit. Then after that, here forgetting of the limit of x, keeping y value 0 in xy plane projection. So 2x becomes 12, then x becomes 6. So these are the limits here. Now x varies from 0 to 6 and y varies from 0 to 12 minus 2x by 3 using the surface. Okay, then this is the formula evaluating double integral r f bar dot n bar dx dy by modulus of n bar dot k bar. Then respective values we are substituting in that. First of all, we are simplifying the inner part. So that is f bar dot n bar becomes 6 by 7, 6z minus 6 plus 3y dot n bar dot k bar becomes 6 by 7 by, but it is coming to the numerator, it becomes 7 by 6 dx dy. So both 6 by 7, 7 by 6 are get cancelled, and the remaining value is 6z minus 6 plus 3 by dx dy. We are evaluating this integral with respect to x and y. So there are one z term is there. So you given surface, we need to calculate this z value. So that z value becomes as 6 in the equation. The given surface, we have directly 6z is there. So that we are writing 6z is equals to 12 minus 2x minus 3y. So this becomes 12 minus 2x minus 3y minus 6 plus 3y. And when the next step we are simplifying this, so it becomes 6 minus 2x dx dy. Now we are evaluating the integrals, that is lower limit, upper limit we are writing, and x value from 0 to 6, y value from 0 to 1 by 3 of 12 minus 2x, and inside we are taking out 2 common out and writing outside. Then inside part of that becomes 3 minus x dy first, then dx. This concept you have in multiple integral. Why? This y variable are depending on, y limits are depending on x limits, so that we need to evaluate y first then x. So with respect to y integration, we'll get, because 3 minus x is constant, so in constant integration becomes y. So y from limits applying 0 to that particular value limit. Then next it becomes 2 into integral x is equals to 0 to 6, 3 minus x, and upper limit substitution, it becomes 1 by 3 of 12 minus 2x into dx, because lower limit is 0. Then again in 12 minus 2x, we are taking 2 common out and writing outside. That becomes 4 by 3, and 3x minus 6x we are multiplying, that becomes 18 minus 3x plus x square. Now integrating this, we'll get 18x minus 9 x square by 2 plus x cube by 3, and applying the limit 0 to 6, it becomes 24. After simplification, it becomes 24. So this is evaluating of the surface integral with one of the projection on xy plane, first octant it is. So this one of the part, and another part is like this, that all the surfaces we need to calculate, and then adding all the surfaces will get the surface integral. For this we are we have one of the question, that is if f bar is equals to 4xz I bar minus y square j bar plus yz k bar, evaluate integral as f bar dot n bar ds, where s is the surface of the cube bounded by x from 0 to a, y from 0 to a, and z from 0 to a. So according to the given limits, the diagram becomes a cube. So this is the diagram, and f bar we need to evaluate according to the each surface. So first of all, we are considering one of the surface here. Okay, Here R1 is equals to first surface. Here we are considering PQRS. Once you see the diagram, then only you are able to understand. For the first problem, first evaluation, PQRS. Sorry, PQAS. So this is the surface PQAS. It is about the x-axis. So here x is the length of this up to from the origin, that is x is equals to a, and it is in ds becomes dy dz, and unit outward drawn normal because it is on x-axis, so that n bar becomes I bar. And limits we need here, y is varying from 0 to a and z is varying to 0 to a. So f bar dot n bar becomes 4x 4xz, because I dot I equals to 1, remaining all 0, so that it becomes 4xz. But we are integrating here with respect to z and y. So x value we need to replace, x is equals to here a, so 4az. So within y from 0 to a, z from 0 to a, integrating 4az dz dy, it becomes z square by 2 integration of z, and applying the limit 0 to a, then we are totally will get constant here, because with respect to y also will get as a. So simplification, it becomes 2a power 4. Similarly, we need to calculate both remaining sides of the cube, surface cube. So directly next R2 we are considering opposite side of the first one. It is OCRB. Here length of the occupation, it is x is equal to 0 here, and ds becomes dy dz. So n bar dot f bar, it becomes 0 because x equals to 0 here. The length of occupying according to the unit word drawn normal is minus I bar here, but x value is from the origin, it is x is equals to 0 to a, so it becomes 0 length here, so that is 0. Similarly, next surface here we are calculating r3 is equals to rbqp. Here z is equals to a, ds becomes dx dy, and unit outward drawn normal is k bar. X and y are varies from 0 to a. So first we calculating f bar dot n bar, it becomes yz, but here y is z is value we are writing, it becomes ay because z is equals to a. Then integrating integral over r3, f double integral surface of r3, f bar dot n bar ds becomes simplification, it becomes a power 4 by 2. Similarly, directly opposite side we are considering, that is z equals to 0 here, ds is same dx dy, and unit outward drawn normal is minus k bar, and f bar dot n bar is minus yz, but z value is 0, then this integral value becomes 0. Next surface, fifth surface here we are considering, that is RPSC, that is y equals to a here, and ds becomes dx dz, and unit outward drawn normal is j bar. X and z is varying from 0 to a. So f bar dot n bar, here we are calculating, that is minus y square will get, that is y, replacing y value as a, so that is minus a square. So this integral value becomes minus a power 4 within the limits of x and z vary from 0 to a. Then directly opposite side of this surface is R6, that is OBQA. Then here y equals to 0, and unit outward drawn normal is minus j bar. Then f bar dot n bar becomes y square, but y value is 0, so this integral value becomes 0. Now total surface we need, for that it is becomes in integral over s, f bar dot n bar ds becomes integral over r1 double integral over r2 plus double integral over r3 up to double integral over r6. So respective values we are substituting and adding, will get the value as here 3a power 4 by 2. This gives total surface of that cube. Yes, ma, don't worry. I will send the PPTs, but E section, this is. So I have your CR number. You don't worry. I'll send PPTs to your CR. Okay. Then we'll enter into the volume integral. This is also and evaluated according to the value is called volume integral. It is denoted by the integral v f bar dot dv. Here f bar is nothing but f1 I bar plus f2 j bar plus f3 k bar and dx dy dz. Integral v is nothing but triple integration of v. This is the formula here. So one of the problem we have here, that is f bar is given as 2xz I bar minus x j bar plus y square k bar. Evaluate integral v f bar dv, where v is the region bounded by the surface x is equals to 0 to 2, y from 0 to 6, z from x square to 4. So this we have to evaluate. For that we are calculating f bar dot dv, that is f bar value, and dv is dx dy dz. We are evaluating according to the, because we have I bar, j bar, k bar terms. So we are separating the I bar integration, j bar integration and k bar integration here. So just simply I am explaining here. Just go through the slides once, then only you able to understand. That is I bar separating triple integration and 2xz dz dy dx, because why we are writing dz first, according to the property of multiple integral, z is limits depending on x limits and y and x are constant limits. First we need to evaluate z first, then constant limit for x and z we can evaluate either x first or y first, that there is no problem. But we need to evaluate this integral compulsory with respect to z first. So that evaluating and writing the j minus j bar of similarly same integral limits and x dz dy dz dx plus k bar same triple integration of y square into dz dy dx. Then first evaluating with respect to z in the next step and substituting limits as x square to 4. Then we'll get the next step as, with the rest, after substituting and simplifying we'll get the equation like this. Then we need to evaluate with respect to y. Y is the no problem, either x or y, no problem, because x and y limits are constant. But in this problem I did as with respect to y, with respect to y, so that the equation becomes like this. Then with respect to x and simplifying, lastly we'll get it is a vector, that is 128 I bar minus 24 j bar minus 384 k bar. So once we need to evaluate carefully, we are splitting in triple integration. I bar I bar of triple integral minus j bar of triple integral plus or minus k bar of triple integral, and evaluating step by step with respect to z, y, x, and applying its limits, we'll get one more vector after simplification. This is a volume integral. So next we are entering to the with this we completed half part of the unit 5, that is line integral, surface integral, volume integral. So in this mostly we have important line integral and surface integral. Most of the problems we have in this for the exam purpose. And then in that line integral, work done problems are very important. Same formula we are evaluating, that is integral over C f bar dot dr bar. That is a work done formula. Dr r bar is nothing but position vector xi bar plus yj bar plus zk bar. Dr bar becomes dxi bar plus dyj bar plus dzk bar. This type of problems you evaluate, simplify more than it is. Um, you able to understand what is work done, then it is important for the final exam also. Then here we have three uh, important theorems, that is Gauss divergence theorem, Green's theorem, and Stokes theorem. So first of the one of the Gauss divergence theorem. In this you have only theorem statement. You don't have proofs. So statements are important, and that are important for the bits also. You have to remember the that is theorem statement, and that for you have, if it is short answers, that time it is short. This theorem statement is important for the short answers, but you don't have that. So this compulsory if it is giving long answers only, that is 15 marks question. This is a very lengthy problems, because we need to evaluate or verify means it is compulsory 15 marks question. Evaluate means that is depending on the problem. Okay, it is my 8 marks question or 7 marks question, like that you will get. Okay, now we are entering to the theorems now. First, Gauss divergence theorem. This Gauss divergence theorem is transformation between surface integral and volume integral. So up to now we completed what is surface integral, what is volume integral. Now we are entering transformation is going on this theorem. So for that we considering S be a closed surface enclosing a volume V. If f bar is a continuously differentiable vector point function, then integral V divergence of f bar dv is equals to integral S f bar dot n bar ds, where n bar is unit outward drawn normal vector at any point of S. This is a one. What is here integral V, that is volume integral, is changing into a integral S, a surface integral. But that is divergent integral V divergence of f bar dv is equals to integral S f bar dot n bar ds. Here f bar is continuously differentiable vector point function, and n bar is unit outward drawn normal vector. This is a theorem statement. Now one of the problem here we are seeing theorems are there. In this three theorems I'll give only one example, because we have more examples, but now today's class we not able to complete that. First of all we are going to one problem in each theorem. So for that, first problem is verify. Verify means we need to verify left hand side and right hand side. This is same like to complete just now we completed surface integral problem, that is cube. Same problem we have, that is evaluating on right hand side, and left hand side we have to evaluate according to the divergence of f bar integral v dv. So verify Gauss divergence theorem for f bar is given like this. Taken over the surface of the cube bounded by the planes x equals to y equals to z is equals to a, and coordinate axis. So coordinate axis means it is indicates lower limits are zeros and upper limits are a. So for that Gauss divergence theorem we have integral S f bar dot n bar ds is equals to integral v del that is divergence of f bar dv. First we are evaluating RHS side, that is integral v del divergence of f bar dv. This is very little, that is RHS side we simply completed, but integral S f bar dot n bar ds, this is cube, so that 6 phases we need to complete surface integral, and then we need to add. So that is just now we completed one of the problem like that, then you able to understand, I think so. Okay, now RHS side divergence, that is divergence of f bar we calculating, that is del is I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z dot and f bar value. Then it becomes dou by dou x of x cube minus yz minus dou by dou y of 2x square y plus dou by dou z of z. So with respect to partial differentiation, then equation becomes x square plus 1. This is divergence of f bar. Then divergence of f bar, we need to evaluate integral v del dot f bar dv. So limits are integral 0 to a, y from 0 to a, z from 0 to a, and here x square plus 1 dx dy dz. Here all the limits are constant, so we can evaluate the integral with respect to any variable first. So with respect to z also no problem, with respect to y also no problem, with respect to z also no problem. But here all the limits are same also, then there is no confusion. But when we are evaluating with respect to any other variable and different limits, then we concentrate on the limits when all the limits are constant. Suppose if we evaluating this integral with respect to y, means we need to apply y limits only. Okay, so that is important there in multiple integral. So here we are evaluating with respect to x first, then it becomes x cubed by 3 plus x, then applying the limits, then with respect to y, then with respect to z, it becomes a power 5 by 3 plus a cube. Thus we consider RHS side ma. With this we completed RHS, but now we need to verify that. So LHS also we need to verify. For that it is the cube, that is same what we have in the previous example. So same cube is there, that is verified. 6 spaces are there, that 6 spaces we need to verify. For this the diagram is necessary for taking each one of the phase. So when we are observing a diagram, first phase here we are taking PQAS. Here the length of x is equals to a, and unit outward drawn normal n bar is equals to I bar. Then limits are this dy dz, and the limits are y from 0 to a, z from 0 to a. Integrating we'll get the value here. Similarly opposite side is OCRB. Here x bar is 0, then it becomes 0. Then one more space here we are considering RPSC, that is unit outward drawn normal is j bar, and y equals to a here, and dy surface is dz dx. Then opposite side is become 0. Similarly z surface if we are considering, that is RBQP, that is a z surface. Here z is equals to a, and unit outward drawn normal is k bar. Then f bar dot n bar within the limits x equals to a, y equals to a, dx dy, will get the surface area here. But next opposite side when we are considering OCSA, unit outward drawn normal n bar equals to minus k bar, but z value is 0, then it becomes 0. So like this we are evaluating f bar dot n bar surface 1, so that is, then surface 1 we got a power 5 minus a power 4 by 4. For surface 2, that is here f bar dot n bar becomes yz ma. Even x equals to 0 means here only x cube term 0 minus yz. So minus of minus plus becomes yz we have. Evaluating this will get as a power 4 by 4. Similarly for the next S3, that is z is equals to a. Here n bar unit outward drawn normal n bar equals to k bar. Then we are integrating, will get as here a cube. Similarly opposite side, that is f bar dot n bar equals to 0 minus z actually, but z equals to 0 this side, so that term totally integral value becomes 0. Then fifth surface, that is equals to PS CR, that is y equals to a, unit outward drawn normal n bar equals to j bar. So f bar dot n bar becomes minus 2x square y, but here y value is a, substituting that minus 2x square within the limits x from 0 to a, z from 0 to a. Integrating will get as minus 2a power 5 by 3. Then last surface OBQA, here y equals to 0 and n bar equals to minus j bar. Then f bar dot n bar becomes 2x square y, but y value is 0, then total value becomes 0, integral value also 0. Then total surface integral we are adding here, all the surfaces, and simplifying will get as a power 5 by 3 plus a cube. This same as triple integral del divergence of f bar dv from equation number 1, because we equation number 1 right hand side we calculated, that is also a power 5 by 3 plus a cube. So both are equal. Hence Gauss divergence theorem is verified. What is Gauss divergence theorem? S is a surface closed interval according to the volume V, and f bar is continuously differentiable vector point function. Then integral V divergence of f bar equals to integral S f bar dot n bar dx ds. Here f bar is n bar is unit outward drawn normal. This theorem statement, according to the theorem statement we are evaluating. Then we'll go for the next theorem. This is similar problems under the Gauss divergence. If we evaluate means only one side we need to evaluate. Let's discuss that problem also. Here one of the evaluate. Once you see here question, evaluate is there. Evaluate integral s f bar dot ds. If f bar is given like this over the tetrahedron bounded by x equals to 0, y equals to 0, z is equals to 0, and the plane x plus y plus z is equals to 1. So evaluate means according to the surface integral it is evaluating. So we have one of the theorem, evaluation under Gauss divergence. It is converted into volume integral, and evaluating is easy because all the tetrahedron sides we need to calculate, and adding it become going to be very large and difficult. So that here what we have, f bar is given as, then we directly calculating divergence of f bar according to the formula of divergence, dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. If this is f bar is f1 I bar plus f2 j bar plus f3 k bar. So directly we'll get the value as 3 by. So integral V, instead of evaluating integral S f bar dot n bar ds, we are evaluating other side, integral V divergence of f bar dv. So limits we need to take because triple integral here we have, but given surface is x plus y plus z is equals to 1. So here in any one of the rule is there, in multiple integral we need to evaluate any surface integral which is depending on 3 variable. First of all we need to evaluate z limits, then where in that after getting the z limits substitute z value is 0, then equation becomes in 2 variables. Then we need to evaluate y limits, then substitute y plus 0, then directly we'll get the x limit. This is the concept. So according to this concept we are evaluating z limits first. Lower limit is already given as 0, then upper limit becomes from the equation x plus y plus z is equals to 1. So z becomes 1 minus x minus y. Then substituting in the z plus 0, then equation becomes x plus y equal to 0 ma. X plus y plus z is equals to 1. So then equation becomes x plus y equal to 1. Then y limits are from that equation 1 minus x is the upper limit, lower limit is 0. Then x plus y equal to 0, x plus y equals to 1, that y plus replacing as 0, x becomes 1. So x varies from 0 to 1. These are the limits. In this way we need to calculate the limits in properties using of multiple integral. Then evaluating this, integral 0 to 1, y from 0 to 1 minus x, z from 1 minus x minus y. The divergence of f bar value is 3y. First we need to evaluate z, then y, then x. Y because z limits are depending on two variables x and y limits are depending on only one variable x, and x limits are constant, so that we need to evaluate x last, z first. So evaluating like this, we'll get the evaluation, and simplifying we'll get the answer as lastly 1 by 8. These are all problems. Now we are entering to the Green's theorem. Here transformation in this Green's theorem, transformation is between line integral and double integral now. It is if S is a closed region in xy plane bounded by a simple closed curve C, and if m and n are continuous functions of x and y having continuous derivatives in R, then integral over C m dx plus n dy is equals to integral over double integral over S dou n by dou x minus dou n by dou y dx dy, where C is traverse in the positive direction. Positive direction is always taken as a anti-clockwise direction. Anti-clockwise direction in this, it is taken as a positive direction. Okay, this is a Green's theorem. Here the transformation is going on. Line integral is changing into double integral. Okay, double integral is converted into line integral in this Green's theorem. So first of all, verification problem we are seeing, because evaluating of both sides, then how you able to understand how to evaluate surface integral and line integral in this problem. Okay, Green's theorem apply. Verify Green's theorem in the plane for integral C 3x square minus 8y square dx plus 4y minus 6xy dy, where C is the region bounded by y is equals to root x and y is equals to x square. So first of all, we comparing this integral C m dx plus n dy. So m becomes 3x square minus 8y square and n becomes 4y minus 6xy. So dou m by dou y becomes minus 16y and dou n by dou x becomes minus 6y. So according to the given equations, while that becomes, it is a parabola. So according to the diagram is like this, and boundary region is 0 to a, that is 0 comma 0 to 1 comma 1. So we have Green's theorem. According to the Green's theorem, we are evaluating surface integral first, that is double integral S dou n by dou x minus dou m by dou y dx dy becomes surface integral of dou n by dou x value is minus 6y minus, but dou m by dou y value is minus 16y, it becomes plus 16y, and simplifying will get as 10 of double integral y dy double integral y y dx dy. So but here careful about the limits, because here lower curve indicates lower limits and upper curve indicates upper limit, but here we need to take one limit as varying limit, one limit is constant limit. That is your wish. X if you are keeping as varying limit, y if you are keeping as constant limit, no problem. But in this problem, we are keeping as x as x limits are constant limits, y limits are varying limits, so that look at here, y limits are 0 to 1. First of all, we think about the low y limits ma. Look at y is the curve under lower curve is y is equals to x square, so we taken as that one as lower limit, and upper curve is y is equals to root x, so that we are taken as upper limit as y is equals to x square to root x. Then this area is within the limit 0 origin to a is equals to 1 comma 1, so x is varying from 0 to 1, and inside y dy first then dx, because we know that is y is varying limit. So according to that, if you are integrating, we'll get the value as 3 by 2. So verification means we need to verify the line integral also. For that we have the line integral along from 0 to a plus a to 0. Okay. So that is I1 plus I2. I1 we are taking as integral 0 to a m dx plus n dy, substituting m value and n value. But according to the diagram, that is y is integral 0 to a. Here we have to take as anti-clockwise direction. 0 to a. So anti-clockwise direction is 0 to a means lower curve first, then upper curve. Lower curve first, upper curve. So along to 0 to a, y is equals to x square is the equation. So that value if we are substituting, then variable we need to change as into one variable. X is varying from 0 to 1 means y variable, y limits we need to change in x. So equation is y is equals to x square. So dy is 2x dy. Then wherever y is there, we replacing as x square. Then equation becomes only one variable, that x, and integrating will get the const value as minus 1. Then similarly I2 we are calculating, that is integral AO, that is comes upper limit, upper curve, that is y is equals to root x, then dy becomes 1 by 2 root dx dy. Then simplifying, and the limits are here varying 1 to 0 ma, x is varying 1 to 0. Then integrating and apply the limits will get the value as 5 by 2. Then adding this I1 and I2 will get the value as 3 by 2. So left hand side and right hand side both are equal. Then it is verified. Green's theorem is verified. What is Green's theorem? Double integral s dou n by dou x is equals to dou n by dou x minus dou m by dou y dx dy is equals to integral over c m dx plus n dy. Here m and n are continuously differentiable functions of x and y. Evaluate means either side we can evaluate. One of the problem is here. Okay, here only one side we are evaluating. Then we'll go for the last theorem, Stokes theorem. Yes, here is a Stokes theorem. Stokes theorem is also same. The transformation is between line integral and surface integral. Here let S be an open surface bounded by a closed non-intersecting curve C. F bar is any differentiable vector point function. Then integral over C f bar dot dr bar is equals to integral S curl f bar dot n bar ds, where C is traverse in the positive direction. Positive direction is nothing but anti-clockwise direction, and n bar is unit outward drawn normal at any point of the surface. Here also, so line integral is changing into surface integral, but inside we have line integral of f bar dot dr bar. This that is work done line integral when we are evaluating problems. This side what we have is integral s curl f bar dot n bar. So one of the problem is there, verify means we need to verify both sides, right hand side and left hand side. So first of all f bar is given, and s is a circular disk, x square plus y square less than or equals to 1 and z equals to 0. Then f bar dot dr bar we are calculating, because r bar we know, and dr bar becomes dx I bar plus dy j bar plus dz k bar. So f bar dot dr bar becomes minus y cube dx plus x cube dy. Then integral over C f bar dot dr bar becomes like this. But here we are taking limits as your circular disk is given, so that it changing into that is polar form, it is easy. But otherwise x square plus y square equals to 1 equation if we are considering, then changing into one other variable and taking the limits of that variable, it becomes difficulty. So that we are changing into polar form, that is x equals to r cos theta, r value is 1, then it becomes cos theta, y equals to sin theta, z becomes 0, theta varies from 0 to 2 pi, this because of the circle, and dx becomes minus sine theta d theta, dy becomes cos theta d theta. And then substituting the value and integrating, we'll get the value as one sided 3 pi by 2. For evaluating the another side, that is we need curl f bar according to the definition of curl, that is determinant of I j k, and evaluating we'll get the value as 3 of x square plus y square of k bar. Here we need to take the projection also, because surface is there, surface integral is there, that projection we are taking on xy plane. Then f bar dot n bar becomes, n bar is unit outward drawn normal on xy plane is k bar, then n bar dot n f bar dot n bar becomes 3x square plus y square dx dy. Then curl f bar and n bar becomes 3 into surface integral of double integral of r x square plus y square dx dy. Then we are writing this one into parametric form equation, then it becomes r square, because x square plus y square equals to r square, and dx dy equals to r dr d theta. This concept you have in Jacobian, using of Jacobian of parametric equations, will get the value as r dr d theta. Then integrating 0 theta varying from 0 to 2 pi and r varying from 0 to 1, because x square plus y square equals to 1, so that evaluating will get the value evaluation also 3 pi by 2. Both RHS and LHS are equal. Then here Stokes theorem is verified. So even Stokes theorem also transformation between line integral and surface integral, but the formula is integral over c f bar dot dr bar is equals to integral s curl f bar dot dr bar. So this is one of the verification problems. So few more problems are also there in these PPTs. If you go through, please go through the problems and solve. These are compulsory. Verification problems are compulsory, directly 15 marks question, or else evaluation means we'll get 8 or 7 mark question. So please go through this. All the three theorems are important. We can't expect which theorem is more important in this. So you go through all the statements, and evaluating of the problems also important here. Okay. With this we completed 15 unit now. So if you have a doubt, please call and take from your CRs. My number is with your CRs. Please go, and if you have any doubts, call me. Okay. I'll send the PPTs. Don't worry about the PPTs, and even keep the kmitonline.com also. If you want to go through the PPTs, means go through that kmitonline.com. Okay.